Thanks, Christian. Thanks, everyone, for coming to my talk. It's a great week. I learned quite a few things from this workshop. So today I'm going to talk about block encoding circuit for pairing Hamiltonian. This work came out of a project funded by the Office of Nuclear Physics at the Department of Energy. It's led by James Berry at Iowa State, and Peter Love at Tufts is involved also. So the goal is to see whether we can develop quantum algorithms to solve many-body nuclear structure problems. We were very fortunate to have graduate student Dee Liu here from Minnesota. He spent a summer at LBL, and he did a lot of the work that I'm going to talk about. We had some discussions with Lane during this work. Ultimate goal is to talk about block encoding circuit. So it's kind of a low level, it's not as low as, implementing on device, but it's still somewhat a low level techniques. So before I get to that, I'll give sort of a background motivation, although for this audience is probably necessary. But I'll do it from a sort of a numerical linear algebra point of view, which is the field that I worked in for a very long time. Then I'll talk a little bit about the general template for writing down the block encoding circuit for sparse matrices. Ultimately, this many-body Hamiltonian is a very sparse matrix, very large, very sparse matrix. We'll try to use that template to see how some of the the sparse matrices can be block encoded, and we can how to write circuit for that. And some of that work is written in this paper, which just got accepted. It's on arXiv also. Then I'll finally talk about how to do this for pairing Hamiltonian. Pairing Hamiltonian is a special type of Hamiltonian that's of interest in nuclear physics. But I'm not going to talk about nuclear physics for this in this talk. This is basically a simplified model that sort of illustrates how we might be able to write down the block encoding circuit for fermionic second quantized Hamiltonian. Okay, so this is a picture of a very sparse matrix. It actually came out of nuclear structure calculation, use sort of what we call truncated configuration interaction. You can see the matrix is very sparse, but it has some structures in it. Okay, so questions how whether we can develop quantum algorithms to do that. So I came from a numerical linear algebra community. So for a long time, we try to solve very large sparse linear algebra problems, use iterative method. Okay, so let me just before I talk about quantum, let's talk a little bit about what we do in the classical world. In iterative method, so we solve linear system, linear least squares problems, eigenvalue problems. In all of the iterative method, more or less, what we do is we try to come up with a polynomial approximation of the matrix. So we construct, approximation of matrix functions. In the case of linear system, we try to approximate a inverse. Least squares, we try to approximate the pseudo-inverse. In eigenvalue problem, to some extent, you can think of it as trying to approximate the delta functions. Okay, so I plotted some of the polynomials down there. One is the polynomial approximation 1 over x, and the other one is the polynomial approximation of delta function centered on eigenvalue, assuming that you know approximately where the eigenvalue is. Okay, so of course doing this on quantum computer is challenging for several reasons. One is that A is generally not unitary, so you have to perform unitary operations on a quantum computer. And also some of the standard linear algebra operations are non-trivial on a quantum computer, things like Saxby, okay? Multiplying a vector and add it to another vector. These things are not easy to do on a quantum computer. So one of the solutions to overcome this difficulty is to use this block encoding idea. So sometimes people also call it unitary dilation, right? So you take a properly scaled matrix, sparse matrix, and embed that into unitary. So for the purpose of this talk, I'm going to assume the matrix I deal with has been properly scaled, okay, with norm less than 1 or something, okay? In addition to block encoding A, you can also block encode the polynomial of A. So this is basically through QSP and quantum singular value transformation. And then if you can do that, you can express the block encoding PA in terms of block encoding the A, and then you can apply that unitary to carefully prepare state and make measurements to get your solution. Okay, so a lot of that is already, people talked about this already. There's some good references that you can look at. So, and before I talk about actually block encoding, I just want to, so I showed this, I think it was last year, there was a quantum linear algebra workshop. So I want to just draw a comparison between the sort of classical and quantum numerical linear algebra, right? So at the theoretical level, I mean, the thing that we do, we rely on polynomial approximation theory, whether you do iterative methods or you want to do block encoding QSP. The method that we typically use in the classical world, power method, is basically an amplification method, and then Chebyshev semi-iterative methods, which is basically try to approximate matrix functions on an interval, okay, continuous interval. And Krylov subspace method is basically constructing approximation in a spectral measure. Okay? And then in the quantum world, we have this block encoding QSP. It's also based on these sort of approximation, but you have to be block encoded into unitary. And in terms of practical things, on the classical computer, we do, we care about how to implement matrix vector multiplication very fast. How do we order the matrix? And to do blocking to take advantage of a memory hierarchy, and how do we factorize a matrix efficiently? On the quantum side, I think the key thing to make this block encoding efficient is to come up with efficient circuit. Okay, so if you don't have a circuit, then you're just talking about block encoding at the very theoretical level. So even before you get to the device, I mean, this is not, I'm not sure how useful it is, okay? And then in terms of evaluating complexity in the classical world, we look at the number of iterations taken by the iterative method. So it often depends on the condition number and error tolerance, right? So this is, and then we also worry about, the cost per iteration. This is usually the flops used in the sparse matrix vector multiplication. Usually, a good efficient algorithm is something that you can get order n complexity, where n is a dimensional matrix, or if you can get to n log n, that's usually considered very efficient. And then we also worry about data movement and things like that. On the quantum world, so the degree of polynomial gives you the query complexity. That also depends on the condition number A and error tolerance. This is very similar to the classical world. And then in terms of cost per iteration, and it's sort of like gate count is the metric, right? So it's a little bit different from flops, but it's more or less similar. And then in terms of data movement, and this is the circuit topology and all these other issues. Okay, so in this talk, I'm going to assume the fault tolerant quantum computing. I'm going to focus on this block encoding QSVT based approach. Okay, so all right. So block encode, how do we block encode a sparse matrix of dimension, say capital N, which is 2 to the lowercase n? So basically, the couple things that we have to do. One is to encode the location of non-zero elements. Okay, so that's usually represented by this function C that maps L and J. So J is the column, jth column of the matrix. L is, you can consider as the Lth non-zero matrix elements in that particular column. So this mapping defines the row index of the Lth non-zero in column J, okay? So that sort of gives you, encodes the structural information, non-zero structural information. And then we use this basically rotation. You take the matrix element and you construct a rotation matrix, and that's how you encode the numerical value of the sparse matrix. And then this rotation is performed by certain control because it's sparse. You have to, control based on the sparsity structure. Okay, so the rotation performed depends on L and J. Okay, because of the control, you need ancilla qubits. You need at least one for rotation, and M, which is usually much less than lowercase n for non-zero index. Okay. So one thing that's sort of, we have to be careful is that you can have an arbitrary sparse structure because that makes the problem difficult because if you have to encode the non-zero structure column by column, and that's already exponentially expensive. Okay, so our goal is to achieve, exponential speed up. So here's a general template that we follow for block encoding S-sparse matrix A. Okay, so there are other ways to block encode, but this template came out of this paper a while ago in 2019. Actually, they provided a more general template, but we sort of simplified this. Ling actually simplified this, and this is basically the structure of the circuit. So let's assume that the matrix is S, has S at most as S non-zero matrix elements per column, where S is 2 to the m. And then the structure, the circuit consists of several layers, and you have a diffusion layer. Basically, takes the zero cat and map it into a superposition of L, and that's used to encode basically all possible non-zero structure in a particular column. And then you have this OC, we call OC, O stands for Oracle. So that basically encodes the mapping from Lj to CLj. Okay, so that gives the row index of the Lth non-zero elements in column J. We can think of this as like a sort of a symbolic operation. So if you work with matrix factorization, there's usually sparse matrix factorization, there's a symbolic factorization and the numerical factorization, and you can think of it as a symbolic operation. And then you need another oracle to encode actually the matrix elements through control rotations, and this you can think of it as a numerical operation. Okay, so to verify that this circuit is actually correct, you can do basically do this operation, and then basically what it does is just take the upper left corner of that unitary and make sure that it's your original matrix you want to block encode. And also this is a useful tool to actually construct the rotations that you need to do the block encoding. Okay, so now I'm going to quickly give a couple examples that we had in the paper. One is this banded circular matrix. It has basically, the matrix is determined by its first column. You just simply permute that. And the non-zero structure can be described by the adjacency graph, which is cyclic in this case. Okay, so the mapping CLJ is basically depends on, so it can be described by adding or subtracting 1 from J. So you can define the CLJ in a number of different ways. You can say, okay, if L is the first, the 0th non-zero matrix element is my subdiagonal, and that's just the J minus 1, and it's modular because it's circular. And then, if it's the first one is just the diagonal elements, and then the second one is the J plus 1. Okay, so then you can actually construct a circuit to implement this, and the circuit, because you're doing add and subtract by 1, this can be implemented. Basically, these are permutation matrices, and you can implement this permutation matrices by basically control sequence of multi-qubit control knots. And then you put these things together, then you can see that this is basically a circuit for 8x8 circular matrix, tridiagonal circular matrix, and you can basically check that everything works out. When L is 0, you basically use R shift to do the subtract by 1, and then if it's diagonal, you do nothing, and if it's subdiagonal, you add 1. So you can verify that the circuit actually does what it's supposed to do. Of course, the OC circuit, the Oracle circuit, is not unique. Actually, it really depends on how you actually define the CJL. Okay, sometimes if you choose a slightly better definition, like this. I mean, this is not much different. It's just that what L equals 0 represent, which non-zero matrix element. So the advantage of this kind of definition, which ultimately gives you the circuit, is that you basically turn the multi-qubit controlled rotation permutation into a single qubit control. So there's some optimization that you can do depending on how you define your CJL function. Okay? And of course, then we can talk about how to do construct the OA circuit, which is to encode the numerical value. We use control rotations. In general, the rotation is determined by both L and J. But for circulant matrix, because all the matrix elements in all the columns are the same, they're just differ by their row positions. So it doesn't really depend on J. So you can actually construct this relatively easily. So this is one way to construct the circuit. And you can verify that these are the angles that you have to construct in order to apply the rotation to get the matrix element. So you get these angles by actually looking at this equation to make sure that you get the right matrix elements on the right position. So I'm not going to go through the arithmetic. It's just simple algebra that you can actually work out all these angles. Okay, so and then you can have, you can also, the OA circuit is not unique also. You can play some tricks to, in this case, to reduce, basically you take out the multi-qubit control and then turn the OA circuit into just a single qubit rotation plus some C naughts. Okay, so that's, and then you can write down the complete circuit that looks like this, and the number of control rotations depending only on the number of non-zeros per column, and the total number of control operations can be implemented in polylog and gates. Okay, so you can also have variations of that. So circular matrix is kind of special, but you can actually say, okay, what about things that are periodic? So Toeplitz matrix, which you have to zero out the corners. You can easily add another circuit component to zero, small number of non-zeros in the matrix. And then you can also modify this to block encode non-Toeplitz banded matrices if there are some columns that don't have some special non-zero matrix elements, and that can be easily done. And you can also extend this to a high-dimensional problem. So the reason that we look at this particular problem is that this is actually one of the, problems that can, have some relevance in, for example, finite difference, finite element calculation, where you have to describe ties on a grid. If you have constant coefficient PDEs, you have uniform grid, and this basically strategy can be applied to encode all these discretized differential operators. Okay? So another problem that I look at is a sparse matrix in which the adjacency, the sparsity structure can be described by a binary tree. So we add an additional node, so the number of nodes or the number of columns is the power of 2. Okay, so this type of class of problem is also important in a sense that it describes matrices with hierarchical structures. Okay, so if you've done something like nested dissections or things like that, you construct these matrices with nested hierarchical structure. So okay, so the position of the non-zero elements depends on both on L and J, and each column has at most 4 non-zeros. And for this particular matrix, I constructed in a way so that all the off diagonals are beta. The diagonals have alpha and gamma depending on where the diagonal elements are. So if the diagonal is on the internal nodes, 1, 2, 3, they're alpha. If they're on the leaf nodes, they're gamma. Okay. So and the CJL can be constructed by this function. So it says basically, so it describes the relationship between the nodes. Okay, so if L is 0 and J is less than 2 to the n minus 1, it's a left child. So the left child is, if you look at the numbers, so they're also, the integer index is 2 times the parent node. Okay, and then if it's the right child, then it's 2J plus 1. Okay, if it's the parent, so the matrix, so these are the the lower triangular part of the matrix, and if you look at the upper triangular matrix, it describes the parent. So the parent of 2 is 1, so that's just 2 divided by 1. And then if you have depends on whether you're on an even or odd column. If you're on an odd column, then you have to subtract 1. 1 is like 3 minus 1 divided by 2. Okay, so all of this relationship can be described by this function, and this function depends on the operations involved. These functions are nothing but just multiply by 2 or add or subtract by 1. Okay. We already know how to add 1 by subtract 1 by using basically permutation, and there are circuits for that. How do we do division, multiplication by 2? And it turns out that you can actually implement this efficiently by a sequence of a swap circuit. Okay, so you can sort of, I'm not going to go through the details, but you can actually verify what happens if you multiply 1 by 2. Okay, so it turns into. One thing that we have to worry a little bit about is that if you have an integer that slightly larger and multiplied by 2, it goes beyond the capital N, which in this case is 8, right? So and then you modulate that by a, and you get another integer, which is at a place that it's not desirable. Okay, so in that case, you want to basically invalidate that operation, and so we use an additional qubit to essentially invalidate these large integers that comes out of multiply by 2. Okay.
Chao?
Yeah.
What do you mean by that can be implemented efficiently?
Okay. So I guess efficiently in terms of the number of control gates. I guess the number of swap operations is poly log n. I guess in that case I consider it to be efficient. Yeah.
I mean, there's something also nice that these are all Clifford operations.
Yeah, right. Yeah. So yeah, I'm not going down to the device level and say, what kind of native gates can be used. So anything that's, a control rotation, control not, I consider it's just a sort of a native gate in this case. So I'm just counting these type of gates. And if it's lowercase n, then I consider the circuit to be efficient in some asymptotic region. Okay, so it's far from sort of the resource estimation. I think it's not quite at the resource estimation level, but asymptotically, yeah.
So indeed, there's some fuzziness in terms of what is easy, but I think some point in the project we thought like localness is kind of important, right? And you don't want to jump not too far away, but also we learned from the discussion with Nathan, certain platforms like Computation, it doesn't quite matter with the involvement. I think these things will change with time.
Yeah. Okay, so let's move on. So once you put all these things together, you can verify that the OC circuit can be constructed in this fashion. So I'm not going to go through all these items. It's in the paper. I just took them out. Basically, depending on what L and J values are, you apply the right operation to get the non-zero matrix elements. So, and then you also in this case you can construct the OA circuit, basically a bunch of control rotations, single multi-qubit control rotations, depending on where the non-zero matrix elements are, whether it's off diagonal or diagonal, and if it's diagonal, whether it's the leaf node or the parent node. So these are all the conditions that you use.
What was the J and the L indexing on that registers?
Huh? What was the
J and the L?
Okay, J is the column index. So in this case is actually just a 8 by 8 matrix. So there's 3 qubits for that, and the L basically tells you the non-zero the L non-zero matrix elements. So in this case, we have at most 4 non-zero matrix elements per column. In principle, you can actually encode that by 2 qubits, but in order to distinguish what type of non-zero matrix elements, as it appears on the binary tree, it's actually more convenient to define 5 types of different non-zero matrix elements, and that's why we use an additional qubit to encode that. It just becomes easier that way. Yeah.
Can you do complex? That would only encode real.
The what?
Can you do complex matrix elements?
In principle, yeah, you can do complex matrix elements, yeah, but it has to be properly scaled. That the angles have to come out to be, I guess, yeah, have to think about that. Yeah.
I've done some similar work where we have a similar structure with these RYs, these multiplexer RYs.
Yeah.
But you can generalize it to complex.
I see.
Rotation.
Okay. Yeah. Okay, so then here's the complete circuit, and again, you know, we just count the number of
This model actually to be posted on
Yeah.
Yeah.
Okay. Yeah, so you count the number of controlled rotations. It depends only on S, which we assume in this case is constant. In the worst case, it's a polynomial of lowercase n. It's independent of the matrix dimension in this case. The number of gates used in all the multiplication and addition, they're also poly n, lowercase n. Okay, so now the rest of the talk will be on the pairing Hamiltonian. So our ultimate goal is to look at the Fermionic Hamiltonian second quantization, which is basically, you know, a sum of creation annihilation operator multiplied by some one-body or two-body interaction. Pairing Hamiltonian is a special case. It basically says just the creation annihilation are combining pairs. Okay, so it's a sort of a special case. It's a simplified model that's used in nuclear physics to model pairwise correlations. They look at nucleons with even nuclears with odd number nucleons or even number of nucleons. But I think for the purpose of this talk is we just view this as a sort of a simplified version of the full Fermionic Hamiltonian, so that I don't have to work with all these 4 creation annihilation operators. So I just look at basically one pair of creation annihilation operator where this A dagger is basically what's called a pseudo creation operator that is the product of the 2 creation operator, 2p and 2p plus 1. And similarly, AQ is the annihilation, pseudo annihilation operator. Okay. So, and I'm also just going to look at the 2-body terms, which is a pseudo one-body term in this pairing Hamiltonian. So, so the structure, a sparsity structure of the Hamiltonian, of course, just depends on just the creation annihilation operator. Right? So the coefficients give you the numerical value. So let's just look at that sparsity structure, and let's represent this J cat, which is the jth column of the Hamiltonian, by just a bit string. And then you see that this pair of creation annihilator applies to a column, a J cat. Okay, it's 0 in most cases, unless the pth bit of J is 0 and the qth bit of J is 1, right? So you can't create anything if something's already there, and you can't annihilate something if there's 0 there, and that's basically the definition of creation annihilation operator. Okay, now if J is, so we consider these J's are invalid invalid if this is true. If J is valid, which means the pth bit is 0 and qth bit is 1, then when you apply the creation annihilation operator, what you do is you basically swap these bits, okay, qubits. So 0 becomes 1, 1 becomes 0, okay? So basically, you see that the creation annihilation pair simply swaps the pth and qubits of J if it's a valid column, okay? So that means we can define the CLJ as basically a swap operation if this condition holds, and then otherwise it's invalid. Okay, and the swap operation, obviously it's a unitary operation, except that you have this condition which you have to implement through some control. Right. So that means basically the OC, you can implement that as control swaps. Okay. So how do we do that? So let's define some notation to simplify things. So I'm going to define the PQ pair by just L, and then this HL is basically AP dagger and Q. Then
So just
yes,
a question on
yeah.
the HL. Maybe this was like 2 slides back where you defined the A's. But should we think of it looked like these A's were made out of products of creation?
Yeah.
So
Right.
does that mean HL is a 2-body?
HL is essentially, it is 2-body, but just sort of simplify things to basically, you can sort of treat it as 1 body.
So like
with
this,
a pairing Hamiltonian. But in general, you can, it's actually 2-body, yeah.
Okay. Yeah, I'm not so familiar
Yeah.
with the pairing Hamiltonian. So that Hamiltonian is not like a mean field Hamiltonian
It's not a mean field, yeah.
because it's a sum of
Yeah,
2-body operators.
yeah, that's right.
It's a little It's a little misleading, right?
Yeah,
Usually,
that's right. Yeah, it's maybe too much of a simplification. But the problem is with if I
like a
just
notation
directly
thing.
with the 2-body, then it becomes really messy. The swaps and control become somewhat messy, so it's difficult to write down. I think it's just simply for the presentation purpose. Yeah, I agree that it's a little bit misleading because if you 1-body, then the mean field. Yeah, you can do the main field.
like usually A
Yeah.
dagger, A,
Right.
that's like,
Yeah.
1-body
Right.
operator.
Yeah. Okay. So so the non-zero structure basically, it's a linear combination, the summation of HLs, which are the AP dagger AQs. So you can think of that actually sort of like a select oracle. So if in the LCU world, so this is basically you can encode that by a select oracle, except that HL here is not necessarily unitary. So what we can do is to implement that, the select, you can actually turn this summation into a product so basically this is a way to implement select oracle. So you basically take the projector tensor product with HL and then plus its complement, okay? So we need some select ancilla qubits to encode L. Is how you select which term, and this is not a unitary yet, but if we add additional ancilla qubit to implement the conditional, we can turn this into basically unitary. So we need additional qubit to invalidate HL times JCat if J doesn't satisfy this condition, okay? So how do we do that? And it actually turns out to be relatively easy. So what we do is we create this validation qubit, okay, so to basically invalidate all the operations that don't give you anything useful. And it's set to be 1-cat by this NOT gate first. And then there's some other ancilla qubits used later to perform control rotations and other things. I'm just going to leave it alone. Nothing's done on that. And then we need a set of selection qubits to essentially implement the select oracle, okay? And I'm also assuming that a diffusion operator has been applied to the 0-cat to create the superposition of all possible selections, okay? Okay. So so this is basically, so you can basically write the select oracle as basically product of a bunch of unitaries. And how does each unitary look? So each unitary UL will look like this. So you would need to have a control on the L to select. And then you also need a set of control on the J to basically validate the operation of HL and J. So you can turn the controlling, and then you use a controlling qubit to actually do the control swap. Okay? The problem is that you cannot, in principle, it's a control operation where control comes from L and J. But you can, control J, perform control swap on J by placing control on J directly. So you need another ancilla qubit to perform, to actually do the control. So when this is a valid operation, which indicated by these controls, you turn the controlling qubit from 0 cat to 1 cat. And then once it's 1, then you can perform the swap. And then in order to do measurements, you have to do the uncompute basically by setting all these ancillars to 0 cat after the control swap. So this is basically, this is what the circuit for UL looks like, okay? And then in the case of when P equals Q, then there's no swap anymore because it's, you know, the destination and the source, they're the same. So basically the circuit just simplifies to basically, you know, some control knot. And then you can also construct the OH circuit. Basically, that encodes the numerical value. So you basically take these control operations and encode them into a product with control rotations. And then each control rotation is basically, it's just a multi-qubit rotation where the angle comes from the non-zero matrix elements. And the control, you only need to place the control on L. You don't need to actually put control on J because that's already taken care of by OC. Okay, so so that's how we actually encode write down the block encoding circuit for the pairing Hamiltonian. This technique can be extended to general fermionic Hamiltonian second quantization. It's a little bit more, the swaps are more complicated, but the basic idea is the same. So, so how do we compare that with LCU? So the LCU writes this Hamiltonian as a linear combination of polys using Jordan or Barbe-Kitaev transformation, and we don't have to go through that. There might be some advantage of doing that. So maybe, you know, in the bosonic case where these transformations are difficult to do, you can still use this technique. The LCU select and prepare oracles to construct the block encoding circuit, but we can actually view OC as basically some version of the select oracle, okay? But the difference is that we don't actually use the transformation. And the OA can be viewed as a way to implement the prepare oracle. So maybe it's easier to view it this way. But we're not sure. More comparison, I think, need to be made. And there's a very nice paper by Kiana back in 2021 that talks about how to block encode select oracle for Fermionic Hamiltonians. So we're still doing some comparisons at the moment. Okay, so let me conclude. Block encoding based quantum linear algebra is practical only if the block encoded matrix can be efficiently decomposed into circuits, right? With polylog n gates. That's sort of our target, but efficient decomposition is possible if the number of unique matrix elements is polylog n, poly n, lowercase n, for a matrix of dimension exponential with respect to n. But this is actually non-trivial for even well-structured matrices. So when we start working on this, we actually struggle quite a bit. Now it becomes clear, how you do this sort of thing. But still, I mean, we've only, described how to do this for a few cases, like, circulant, which has some relevance to finite difference, finite element, binary tree, which is matrices with hierarchical structures. Second quantized Hamiltonian. But I think what's lacking is maybe perhaps an even more general strategy. I think right now we're just doing this case by case. But I think it would be helpful to develop some more general principles and strategies and to construct efficient circuits for sparse matrices. That's it. Thanks.